Today we're gonna come back to the ending center lecture, so quantum speed lecture, and we're gonna talk about Rabi oscillation. This is the most fundamental topics in quantum mechanics, yet it is very important. It is of essential importance in quantum information. So it is very important that you pay attention to this. Right. So let's come back to MV center. In MV center, we talk about qubits, right? MV qubits. We have a ground state, we have an excited state, right? And we talk about driving it with microwave. Did we talk about driving it with microwave? we talked about preparing it in a ground state, right? Using laser light. Did we talk about driving it? Probably not. Okay, we didn't. All right. So come back to the ground state, excited state. Physically, this is implemented by the m equal to 0 state in the ground state triplet, and this could be m equal to 1 or plus 1. Let me just say minus 1. Minus 1 or plus 1. So let me say m equal to plus 1, right? And there's another one, plus 1. So this is all ground state, right? All ground state triplet. Right. Actually, right. I need to do this. And we talked about this splitting is due to so basically this is splitting. Sorry. Originally, in principle, they are all basically degenerate. That means all three states have the same energy, right? But because of this spin interaction between the two electrons, right? Remember, this is a two electron spin. This is a two electron state, not a single electron state. So we have two electron here, two electron here, two electron here. They are just in different orientations. Remember? And because of the two electrons interact with each other magnetically, so we have this zero field splitting, and this splitting has a frequency, or this splitting matches with a photon energy of for a photon of frequency 2.875 gigahertz. Yeah. Now, if on top of this we apply, all right. I think last time we were left here. Okay, great. So this is good. Because the last time I remember you asked about there being two states. Remember I asked you how many, in one of the quiz I asked you how many qubits can we have in this system, right? And the answer is two pairs of qubit states. Yeah. So, and I think Clement asked, then how do I know which state I drive my population to? Because I have two states that are degenerate, and if I apply the same this photon energy, how do I know if I go here or go here? Right? Correct? The answer is yes. You actually go both. You go to both states because it's degenerate. And physically, this is a pretty interesting system to study. But if we want to use this as a quantum bit, as a qubit, then we want to limit ourselves to two states only, right? Because we want one state to represent 1 and the other state to represent 0. One state to represent 0 and the other state to represent 1. And we want to have superposition between these two states instead of three states. Yeah? Okay. So so this is not a qubit state yet, not a qubit system yet. Okay? So this is still this MV center. Yes? Okay. So how do we turn this in from MV center ground state thing to MV qubit? How do we make use of it? Answer is simple. You apply an external magnetic field. Okay? Yes?
An NVQ, is it a state where the states can be like any combination of 0 and 1?
Yes.
Okay.
Yeah, that's what qubit means. But a classical bit can only be 0 or 1.
Yeah.
One of the two, cannot be both. But quantum bit, qubit, can be in a superposition of both. And today we're going to talk about that. How do we prepare in a superposition? Okay? And that's why this comes here. But first, let's think a little bit how we're going to change this 3-state system into a 2-state system. Okay, so we already have 2 states here. This 2 and this 3 states. Now, how we want to change it into a 2-state qubit system. How do we do that? Well, the answer is we apply a magnetic field. Okay, so if we just apply a magnetic field around, so this is the NV center diamond, right? And we have, I use, this spin thing to represent it, but it's really not. So just think of this as N and V, okay? Think of this as like a diatomic molecule, okay? We simply apply a magnetic field, a uniform magnetic field around it, okay? And this magnetic field will talk to this and this state, but not this state. Anybody knows why? Okay, let me give you a hint. This is that too. Give you a hint. Okay, that's my hint. M equal to 1 and M equal to minus plus 1. So I'm saying the magnetic field will talk to these 2 states, but not this state. Okay, not an N equal 0 state, but it will be N equal plus and minus 1. Do you know why?
Because they are at
N. What's the N mean?
the magnetic torque.
Close. Okay. Anybody remember what the orientation is? So we have 2 electron systems, right? Okay. And this is a triplet state, right? Okay. So a triplet state has this. There are 3 possible ways for their relative orientation, right? They either go up, up, or down, down, or 1 up, 1 down, or the other up, the other down, right? So actually 4 possible orientation, but these 2 are basically equivalent. Okay? So this is a triplet. Triplet is 3 states. And which one is this? So this is like, it sounds English homework. It has pictures on one side and vocabularies on the other side. And he has to make things. Okay. And we invite the bravest person among you all. That is, I think that's you. Okay, could you help me make links? Just take a while, I guess. That's okay. You're just a big touch. Okay, thank you very much.
Thank you.
All right. Well, this is perfect. Correct. So this is the angle 1. This is -1. This is 0. Okay. What does this mean? This means when I have the two spins lined up, they have a total magnetic moment of 1. Okay. This is a total magnetic moment. Okay. Let me just say UE or 2UE. Okay. And here in this case, they have a total magnetic moment of -2UE. Yes. And in this case, the magnetic moment cancels each other. Okay, so this has 0 magnetic moment. Okay. Now, so you can see this as basically an entity of a single spin. Okay. So physically, you can picture it as like one particle with a big spin that have a magnetic moment of 2 newton. Yeah. And this is when that spin is pointing up, and this is when that spin is pointing down. Okay. And this is just basically. So the effective picture of this is it is a particle without any spin. Without any spin. So it is not talk. Since it does not have any magnetic moment, it has not no spin, it does not talk to the B field. Right? Because the interaction, the energy is minus mu dot B0. This is the energy. This is the magnetic energy. Okay? Magnetic energy. This is why when you have two magnets, so we have polarities for each magnet, right? When you have a magnet here and you put another magnet close to it, there is a tendency for this magnet to flip. Okay? To flip so that they are in opposite order. Yeah? And you know why for this? That is because the field. So if the spin is this way, sorry, the magnetic moment is this way, the field is the opposite, like adjacent to it. So this is the field. So the field goes down. Okay? So when you bring another spin to here in the same orientation, let me see. Is this right? Maybe this is wrong. Maybe I do the opposite. Let me see. Yeah. Okay. The opposite. Yeah. Right. So when you bring this in close to this magnet, you find there is a tendency for this magnet to flip. Like this, right? And the reason is because the magnetic moment of this magnet 2, so this is magnet 1, and this is magnet 2. The magnetic moment of magnet, okay, this is 1, and this is 2. Okay, and this is the field of this magnet, okay? So in this orientation, they are opposite each other, right? It is not aligned with a B field. So according to what I just gave you there, the magnetic energy here, this is a negative value. So the magnetic energy is a positive value. But if it flipped to the other orientation, then in this case, in this case, the magnet, they are aligned, right? When you flipped, the moment is aligned with the field. Yeah. So this will be a positive value, and this will be negative. The total energy is negative value. Negative means it's lower compared to the other location. Yeah. So this is high energy state or high energy configuration. This is the low energy configuration. So naturally, you will want to go from here to here. Okay, from high to low. Okay. So you know that there is, if energy goes like this, if the potential energy goes like this, then you can calculate the force on the potential energy, right? And so there will be a kind of a magnetic force that affiliate this flipping, that will act on the magnet and flip it from high energy state to low energy state. The force will guide it from high energy state to low energy state. Okay. So in this case, it's the same. It is the same way. We have a mag. So plus one means plus one means a long field. Minus one means I'm not sure. Okay, so if our field is pointing up, okay, and plus one means pointing up, and minus one means pointing down. Yes. Each one of them will be in a lower energy state. Positive one is since, right? So this is probably wrong. Okay. Positive one is minus one. Yeah, so it will move from the degenerate energy down by this much magnetic potential energy. And on the other hand, the minus one will move up, right? So this energy difference is what we call the Zeeman splitting energy. Zeeman. Is that right? I'm not sure. Is this how Zeeman is spelled? Z-E-E.
That one.
Is this the correct spelling? Okay, great. Zeeman splitting. Okay. Zeeman splitting. Okay, and this splitting is proportional. This splitting corresponds to a frequency, right? And this frequency is proportional to the strength of the B field. Okay. So when we have this, then we break the degeneracy, and we can pick one of them to work with 0 as a cubic pair. Alternatively, we can try this, but our population are all here, and when it relaxes, it will also be here. So it's better to just use this, the A equals 0 state, and pick one of the state as the steady state. And in this case, we pick the plus one. Okay. So n equal to plus one. So using an energy, an external B field, and Zeeman splitting, we separate this. We isolate one of those states, and then use it to couple with the ground state and form a qubit system. And that's how we do it. Okay, great. Now, so we have done that, and now we start with, again, that diagram, MB qubit, E and G. and E here is n⁻⁴. Yeah. Ian, can you check if this is correct? I'm not sure. I'm a little doubtful. Maybe it's right. Okay, I just always assume the higher one is the +1. Yeah. Okay, so now how do we drive? Okay, now we are in the ground state. Yeah, a ground state is not very useful. What is useful is if we can at least drive it to the, if we can at least make it to the excited state, we have at least 2 states to switch between, right? So how do we make, I mean, even classical bit can do this. How do we flip the bit from the 0 state to the 1 state? How do we flip it? Well, since there is an energy gap, the obvious way to do it is to provide an energy. Okay? To provide an energy of microwave photon, because this frequency is microwave. Yeah? Provide energy of microwave photon, and then we should be able to, when the electron absorbs the energy, it will jump, make this jump from 0 to 1. Yes. Okay. And this transition is of course, well, so this is your initial state, this is your final state. Okay? And how do we predict, or how do we know how long I need to turn on my, because I mean, basically we don't have a single photon microwave source, right? We probably have a single photon optical wave source, laser wave source, but we don't have a microwave single photon source, right? So how do we drive this there? If we, or maybe let me put it this way. If I turn on my microwave, what do you think will happen? If this is the population. If this is the population of the ground state, or population of the excited state, okay? Now, I start with 0. And if I drive my, okay, this is a great start. If I drive it, do you think, okay, this is 1, okay, 100%. Here, do you think it will go like this? Or do you think it will go like this? This being 0.5, so 50%.
Classical?
Huh?
Classical.
Classical?
If it's quantum.
I mean, is the microwave in the same frequency?
Yes. On resonance.
Sorry?
On resonance. On resonance means the applied drive oscillate at the same frequency as the oscillator. That's the, yeah, your resonator. So it's on resonance, same frequency, correct? The Rabi oscillation, okay, where does the actor come from? Okay.
If the frequency is the perfect one, almost all the atoms should absorb it, right? And
You're right.
become the first excited state.
Yeah. Okay, that's great. So there's no reason for the photon not to absorb it, right? For any reason not for this end reason not to absorb the microwave. If I drive it long enough, there should be 100% chance for it to go up. Correct? Yes. Okay, great. Now the question is, after it almost reached to the top. Okay, let's say this is this time T0, capital T0. At this time it reached the top. If I continue to drive it, what happens? Does it stay there? Does it stay there? Mark, does it stay there? If I drive it to 100%, and then I keep on my microwave, I keep showing microwave, then does it respond or does it saturate? Does it not respond at all? Why?
I don't know. But I remember that's what we saw.
Yeah, that's what textbooks told you.
Yeah.
But you don't know why. I want you to think.
Just as stimulation. Because the density matrix tells us.
Density matrix. Wow, man. Where's that word come from? Okay.
Is the question why the atoms excite energy and go back to the ground state?
I am just asking what the behavior would this be? So if I successfully manage to put in enough energy to the system, so I drive it for a substantial amount of time, and the energy is absorbed to the system, and now it's in the first excited state, right? Does continuous illumination of the microwave do anything to it? Well, if I keep my microwave on, would it have any effect? Will it have any further effect? In this period, yes, it will pump energy into the system, so it will go up. But then afterward, does continual pumping still do anything?
Yes.
I would say, the electrons, when they are in the first excited state, then they no longer can absorb the energy from the microwave, so they will fall down to the ground state again. But then
That's correct. So
But then they
natural
can-
relaxation,
yeah.
right? That natural relaxation, yes, it does do that. But typically, this only happen. Let me just draw this dotted line. Okay. This happens. So if I stop my microwave here, yes, after a long period of time, it does go down to ground, and this is a natural decay or natural relaxation. Okay? Correct. You're right. But we're not there yet. So I'm talking about like immediately after. So let's say if this takes, I don't know, 1 millisecond to happen. Okay? And this is like 100 nanosecond. Okay? We are still pretty far from relaxation. If I continue my drive to the system, what will happen? Does it saturate and not do nothing? Or will it respond to my drive? Respond? What do you think? Don't give me a textbook answer.
I think it's stay there.
It does stay there.
It
It
makes
makes
no
sense.
It makes no sense to drop. To me.
I like that. Right. What do you think? What do you think?
I think that they will de-excite, but then they will excite again.
Why would it be excite?
Perturbation?
I mean, that's
What?
like
Perturbation.
Perturbation.
What's perturbation?
that's a philosophical question.
It's a philosophical question.
Everything decays.
Okay.
Like, why do you die?
But that you're talking about this, and I have to acknowledge that. Yes, this what happened after a long time. I'm talking about immediately after 100 nanosecond.
Is this a two-state system?
This is a two-state system, correct?
And the microwaves is still there, right?
Yeah. So I just
The
keep
energy is still there.
I just
That
keep-
doesn't make sense.
keep pumping it, right? So if you have a little, I don't know, a little kid, and then you keep feeding chocolate to the kid,
Yeah.
what would the kid do? Excite. And then just stays happy forever, right?
Yeah.
You would just keep enjoying chocolate. So what would this do? I mean, there's no, it cannot go up because this is already the ceiling, this is the top. There are only two scenarios. Either it goes down or it stays. Which one? One or two? It will be. What do you think, Mark? Stay. What do you think?
I think there's no way that, I can think of something that restrict the upper state to, restrict the upper state from absorbing the energy.
I mean, it does
So-
not have any upper energy state to go to. So it cannot absorb any more energy. Right? If this is like a series of ladder, yes, it can go up. But this is not, this is a two level system. So there's no upper state it can go to absorb more energy.
I think the population will stay.
Alright. I would say the only logical answer to this question at this moment is that it will stay. The only logical answer to this question at this moment is that it will stay. Okay? Yeah? Because we have not talked about anything else but the qubit and the drive. Yeah? Okay. But this is not what we see in the experiment. What we see in the experiment is this. It goes down. Why is that? That's pretty strange, isn't it? Okay. The reason is so in the previous lecture we talked about photon states, right? Photon statistics, right? We talk about intensity being the photon number. Intensity is related to the photon number operator, correct? Alright, so if you want to calculate the energy, we want to measure the energy. Yes? Then we use the photon number operator, right? And then what kind of intensity, how much intensity we'll have depends on the states, right? If we have a single photon state, then our energy is just like 1 unit of our intensity is like 1 unit of the photons, right? But if we have a laser, or in this case, a microwave, this and this will be basically that. And in the photon statistics, they correspond So this is the photon population, right? Yeah, so this is like the probability of landing on a 2 photon state, 3 photon state, 4 photon state, right? And this is the average number. Okay, so the expectation value, how many photons you get out of this state, in average, if you take a lot of measurements, in average you get this number. Okay, so this number is that, and that's the square root of alpha. Okay, so alpha means, so, and anyway, what I'm trying to say is, when you shine the laser, although I drove this, in fact, it's actually a lot of them, a lot of photons. Yeah? In fact, it's actually a lot of photons. And can this absorb more than 1 photon? Can the system absorb more than 1 photon? If each photon has a photon energy that is identical to this energy gap, can this system absorb more than 1 photon? Yes, it can absorb 1 photon, correct. 1 photon. Yes, thank you very much. I'm here. And then now the next photon come. Okay, so now I'm here. Okay, so this is like T1, T0. T0 equal to T0, right? And this equal to T0 plus a little time after. Okay, so here a little time after. Afterward. Another photon came. This is the question I was asking. Does this photon, will this photon has any effect on the electron? No. Probably not, because there's no higher state to go to, right? It cannot absorb. Okay. But so we would naturally expect this one, flat line, saturation. But instead we see this, we say go down. What's the reason for it? What does that mean? Why would you drive? If you heard of the Einstein AB coefficient, this is exactly that problem that Einstein was thinking about. Okay, at that time, people have very little knowledge about the quantum nature of the electromagnetic field. They have some knowledge about quantum atomic system, but as for the electromagnetic field, they really don't know much about its quantum property. Okay. Yes.
Is this when stimulated emission happens?
Yes. Exactly.
I've been wondering why.
Yeah. So long story short, there are 2 decay processes. One is called the spontaneous emission. Spontaneous emission, and these 2 are basically the same process. Spontaneous emission, if you think about the electromagnetic field being a quantized state, then in its ground state, the so-called vacuum state, does it has energy or not? Yes. If you take the electric field, average, it is of course 0. But if you take the field width, the fluctuation, is it 0? No, it is not 0. Okay, it fluctuates. Why does it fluctuate? A physical picture would be because photons pop out from the electromagnetic field for a long time, but for a short time, and then it goes back. So it's like fish jumping out of the sea level, or dolphins. For a short moment, and it dives back. Okay, so you can think of photons like that, and they are like little fish. They pop out from the sea, and they show up for a very brief moment, and then pop back. And they dive back to the sea. Okay. So So if this is the electromagnetic field, this is the photon which you can absorb. This is an excitation, right? So like if you throw a rock to a pond and water splashes, and you see the little water drop come out. Okay, those are like the photons. Okay. But they go back very soon. Yeah. So they come out for a brief moment and they go back. So in average, the electromagnetic field due to those photons is zero in average, but fluctuation is not. Okay? Now, so for a brief moment, yes, there can be photon popping out of the vacuum. Something out of nothing, essentially. And this photon, for this brief moment, can actually interact with matter. This is called a vacuum effect. Okay? And there are a lot of other vacuum effects that are magical, but this is the most prominent one. So the vacuum photon comes, and then it will stimulate the system, emit the system. So the system will be prone to de-excite, and because photons are bosons, right? So it will be de-excited and then emit a photon that is of the same mode as this vacuum photon. Okay, this is called the spontaneous emission or spontaneous decay. Okay. Okay. Now, if we have a real photon, such as so if this guy is here, if we have a real photon coming, so this is this. The same process will happen. The stimulated emission will drive the system down too. Okay? And let me just use green. Okay. All right. So because of the stimulated emission, the system is prone to release its energy, and then it will go down to the ground state, and then excited again, and then go down, and then excited again, and then go down. Correct? All right. So this is called Rabi oscillation. This oscillatory behavior in the population as you continue drive the system within the microwave. This is called Rabi oscillation. Okay.
I have a question. So, the probability that the photon drops from the upper state to the lower state, what is the difference between this probability and the natural decay that?
There's no actual difference.
Yeah, then why you draw it like?
Oh, good. That's a good question. Very good question. Yeah. So Tim is asking why, if they are fundamentally the same, why one takes so long and the other is so fast?
Because that's the time scale, right?
Right. Correct. You're right. This takes as much time as it drives it. So this is 100. If this is 100 nanosecond, this is another 1 nanosecond. Okay? But this is like what? Millisecond. So that's for lack of sleep. 1 millisecond. Completely two different time scales. And that's a very good question. That's a good how to say, you pick the right problem. Why are they, if the fundamental mechanism is the same, stimulated emission, so basically everything is stimulated emission, just one from the real photon and the other from the virtual photon, okay? We call it the virtual. It's still real, by the way, just people sometimes call it virtual photon because it doesn't exist indefinitely. It just exists for a while and then it goes back to the vacuum state, okay? Why does one take so long and the other is so fast?
It's all intensity of the photon.
Correct.
What did you say?
Intensity.
Intensity of the photon, the number of the photon. The chance of a photon coming to here from the vacuum is small, right? Because I told you that it only pops out once in a while. So you have to wait. And when you don't know when it will pops out. Sometimes you wait for a long time, sometimes you wait for a short time, but in average, it takes 1 millisecond, okay, for one to pop out for such a frequency, okay. But here we have like a bunch of them right in the vicinity because we apply a microwave drive, okay. So this is just a matter of chance, okay, because we have a lot of photons here, so there's a big chance for it to absorb or stimulate emit. Yes? And this will actually link to the next point I want to talk about. All right, so we're good here. Yes? Thank you for the question. Now,
I want to
all right, now I talk about time. Okay, not too bad. Only 1 hour. Only 1 hour has passed. Almost done. I'm just sinking into the second part. So I have one final remark before we transition. Okay. So this behavior can be obtained. I mean, we just kind of argue our way through it, right? Using known physical mechanism, and this is what we expect. When we solve the Schrödinger equation, I won't go into the detail of how we solve the Schrödinger equation. So you can find that in any introductory quantum mechanics textbook. Just look for Rabi oscillation. We can solve it, and then the population is the ground, and this is the excited. They are sorry. Wrong. Yeah. Not wrong. And 1 minus. this is the solution. And here, this is fine. That's this. Okay. All right. Why do I want to show you this? Didn't we agree? We agree that this is a non-calculus spaced lecture. Okay. The reason I want to show you this is because I want you to see the dependence. So let's focus on this one because this one has a simpler form. And believe it or not, this can be turned into something like this. Okay? Why do I know that? Because the sum of both must equal to 1. So you can go back and check if this is true. It should. Alright. But basically what this says is the excited state. The excited states will go like this. And the ground state will go like the ground state was 1 to begin with. Out of phase. 180-degree out of phase. Yeah? So this will be the sine function. Right? Sine function. Oh, so sorry, it's just, I'm sorry. It's just sine there. Sine, correct. And this will be the sine function. Good. Yes. Am I missing anything? This is called Rabi frequency. This is called generalized Rabi frequency. Don't worry about this, it's just names. Generalized Rabi frequency. I give you these names because the menu will have names, and it's better to have some knowledge of what people. So this difference between drive and the resonance frequency, by the way, this is called omega 0. This is called detuning. How far is your drive frequency away from the natural, from the resonance frequency? That's called detuning. Okay. Okay, let's see what this means. This means it will oscillate at a period of omega 2 pi over omega. Do you agree? This is the sine square function, and the frequency here is omega over 2. Yeah. When you have sine omega over 2, the period is, say, this. Yeah. This one period. Yes? And when you have sine, don't have to write. Okay. When you have sine square, then become like this, right? And the period become half, or the frequency is double. Okay? So the period become half, or effectively the frequency is doubled. Correct? Okay, so the double frequency is omega. Yeah? saying this oscillation period is 2 pi over omega. Okay. The excited state will go like this. The ground state is 1 minus intensity of the excited state population here, so it will also go like this. Yeah? Okay, great. Now, there are two features I want you to pay attention to. The period here. If I write it out, it depends on this. It depends on this. Okay. So what's the Rabi frequency? The Rabi frequency basically is proportional to the coupling between the excited state and the ground state. The coupling strength. Okay? So in other words, how strong does this couple to a magnetic field? And the magnetic field, of course, is the microwave. It's from the microwave. So how strong that is. So this is of course not B0. B0 is what caused the splitting. Now we're talking about a microwave. So I will use B microwave. Okay? So the microwave intensity or the microwave strength. The harder you drive the microwave, the larger this Rabi frequency. Okay? And when we are driving it on resonance, there's no difference between the generalized Rabi frequency and the Rabi frequency. They're the same. Okay? And in that case, this will be just that. Or this will be proportional to 2 pi. Sorry, B microwave strength. Okay? Yeah? Alright. So that's one. When we increase the microwave strength, this becomes shorter or longer? Shorter. Okay, good. Why is that?
High power.
High power.
High energy oscillation at fast.
High energy oscillation is fast. Not exactly right, because the oscillation actually is fixed. It's oscillating in the natural frequency, right? This is by no chance. And the okay. So if you take the natural frequency, which is 2.875 gigahertz. Yeah? Let's just do a quick calculation. 1 over 2.75 gigahertz. How much is that? 2.875 is close to 3. So this is close to 3, right? And gigahertz is nanosecond. So this is 0.3 nanosecond. That's how fast this resonator is. So it's really, really fast. Okay? And as I said, this is usually at the time scale of 100 nanoseconds. So why does it take so long? So this oscillation and that oscillation are not the same thing. Okay? Obviously, the time scale is completely different. And this is this is oscillating at a fixed rate. This oscillation depends on my drive strength and also how far I'm away from the resonance, frequency-wise. Okay, so this two are two different. So this Rabi oscillation and this natural oscillation are two different things. Okay, and Rabi oscillation you can think of as an energy oscillation because this is the ground state population. This is what the excited state population, right? So if you ask what the energy of the system is, right? You have the energy of the ground state times the population of the ground state, and the energy of the excited state times the population of the excited state, right? Okay. So you can think of this as the energy of the system is being oscillated. So the Rabi oscillation is an energy oscillation instead of, or population oscillation instead of the real motion, the motion of the quantum wave. Okay, so this is more like the motion of the quantum wave, and this is the energy of the quantum system. Okay, so now the question is, when we have a higher drive, stronger microwave, why does this go down? Why does the period goes down? Or let me use, since I'm talking about energy of the system, it's probably more more intuitive if we just focus on the excited state, okay? Because when the excited state is up, the energy of the system is up, right? So let's talk about the excited state only. Let's focus on that.
Sure.
They're opposite each other, so you wouldn't lose any generality. If I increase, again, if I increase this, this becomes this. Shorter. Why is that? Number of photons are being, there are more number of photons in the system, right? So there's a higher chance for it to absorb photons, or a higher chance for it to be excited, stimulate emission, right? Higher chance. So this has to be, so this Rabi oscillation also answered, so this power dependence also answers your question. So for the B field from the vacuum system is very, very small. The vacuum fluctuation, the scale, the amplitude of vacuum fluctuation in the B field is super, super small as compared to the B field strength in a microwave drive, okay? And that's why the time scale is completely different. The other is much slower, and this one is much faster, okay? So, since there's a higher chance, so if you focus on this part, if there are more photons in the system, there's a higher chance. If I wait for same amount of time, right? There's a higher chance for me to absorb a photon when the microwave power is strong. Okay, and lower chance for me to absorb the photon when the microwave power is slow. Okay, and here too. From my peak point, from my apex, if I wait also for the same amount of time, there's a higher chance for me to release a photon. But there's a lower chance for me to release a photon if the power is low. Okay? So now you understand the power dependence. You understand where this comes from. Good, you have a physical picture for that, right? How about this one? How about this one? If I drive it at a frequency that's slightly different or a lot different from its resonance, the effect is the same. Isn't that amazing? Right? If this is 0, of course, I don't need to worry about it. But if I have finite detuning, that means I'm away from the resonance. The effect is the same as if I would drive this with more photons. The periods become shorter. If I wait the same amount of time, okay, there's a higher chance for me to go or up, then yeah, that's right. What is that? Okay, so this is, I want you to think about this because when you apply the formula, you don't think about things like this, but this is a physics. Okay, the formula is just math. That is just supposed to represent physics. If we spend enough time to think about physics, we will know both. Okay, we cannot just know the math. We need to know both. So with finite tuning, why is the period also shorter? It's really possible, right? Even my last year didn't know the answer. I mean, from the last semester. I mean, we use this a lot, but we seldom think about it. So remember, every term in the physics formula has a meaning, has a picture corresponding to it. And it's your job to find it out. Yeah, sometimes the textbook won't give you that because the author doesn't know either. But it is important for us to think, ponder upon all this dependence and think about why. Think about a physical picture, a physical mechanism that make this dependence happen. Okay? All right. So to tell you the truth, I deceive you a little bit with this picture here. I deceive you a little bit with this picture here. When this finite tuning, when there's finite tuning, I didn't really deceive you, but I didn't give you the full picture. This is the maximum. So this defines the maximum population you can drive to, right? Yeah. Okay. When there's zero detuning, omega and omega naught is the same. So we can go to 1. So this picture is correct. But when there's finite detuning, right? This becomes this, and this is a number that's less than 1. By the way, this is the Lorentz line shape. This is the Lorentz function. Okay. But anyway, it becomes less than 1. Okay. So if I would have to draw this, it is actually goes like this. Okay? So yes, it is shorter, but it is also lower. Okay? It is shorter, but it's also lower. So if you look at this picture, it is perhaps easier to understand why a detuning will give a shorter period. Okay, let's look at this again. When I have a detuning, then after I wait for the same amount of time, yeah, the drive that is on resonance, suppose the power is the same. The drive that is on resonance will have a higher population, higher chance to be excited. And the detuned drive will give a lower chance for the system to be excited, correct? So high, low, and this is high. And this is this. Okay. So this gives us a clue. When you detune, after you start driving it and you wait for a certain amount of time, there's a lower chance for your for your system to be drive to the upper state. That makes sense, right? Because we know when we are not on resonance, our drive is less effective or less efficient. Okay. What would be so that naturally makes sense to us, right? And what would help us is this picture of a classical harmonic oscillator. This is 3. Almost done. There's a reason we learn about classical harmonic oscillator because it's so ubiquitous. When we drive it, so say we have a rope and it's attached to this oscillator and we drive it like this, right? Oscillate, and this is my hand. Okay, my hand oscillate. Yes, we're in sync. I'm pumping energy into the system. It's like pushing a swing, right? Now, if I push it a little too fast, yeah? If I push it, if the frequency is a little different, and I push it a little too fast than I'm supposed to, what would happen? At some point, instead of pushing it, I will be pushing against it, right? Because the two swings are not synced, right? If they are synced, if they are the same frequency, I'm always pushing the swing. I'm swinging my hand with the swing. I'm always pushing it. I'm always pushing it. But I'm always pushing it. But if this goes a little too fast, right? And there's a little gap in time. Then over time, this gap will become bigger and bigger and bigger. Okay? And at some point, it will be opposite. Right? It will be opposite to the direction of the swing. I'll be pushing it, or I'll be pushing against it instead of pushing it. Yeah? So that's what happens when you have a little frequency slip. Yes? Okay. So that's why it becomes less effective. Your push becomes less effective because half of the time you're pushing against it. You're doing negative work to the system. You're taking energy from the system instead of continuously putting energy into the system. Yeah? And when this is small, you have to wait for a while for this to happen. But if this is large, if this gap is large, okay? If this gap is large, like this large, then it won't take long before you find yourself pushing against the swing. So if you wait for a fixed amount of time, say 1 minute, there's more chance, like there are more incidents for you to push against the spring if you have a larger frequency or a larger frequency tuning or larger time gap, time split compared to a smaller time split, right? So this like happens. This first one happens once, but this will probably happen 3 times. So when you have larger detuning, you push against it more frequently, and that takes away energy from the system, and that limits the system from reaching to a high energy state. Yes? Compared to a small detuning. That's what. So that explains why there's a drop here. It go out of sync. Okay? After a fixed amount of time, it go out of sync, so it does not follow the drive anymore. It go out of the sync, so it's not as effective, and you can now reach a high state, a high energy state, like a high energy configuration. A high energy state, like when you're on resonance. Okay? So that explains why it is in the denominator, and why, and this indeed is dependence. All right, so a classical oscillator picture helps. Okay, great. Now, final point, we're done with this. Well, 1.5 hours. It won't take long. The next one won't take long. Now, I want you to consider this. So, if we have 2 buckets, one called the ground state, the other called the excited state. And according to this behavior, it looks like I can take population from here to here, right? But the same drive, so from the physical point of view, the same drive can also take particles from here to here. So if I have marbles, you know what marbles is, right? Marbles, the little glass ball. If I have marbles, originally all piled up in the ground state bucket, think of this as population. Right? Or you can think of it as the MV center in the diamond. Okay? I pump one MV center to the excited state, I pump 2 MV center to the excited state, I pump 3 MV center to the excited state, right? And then here I pump 1 MV center back, so I take 1 MV center from the ground state, I take the other MV center from the ground state. Okay. This picture basically has the same mechanism as what we described here. An excitation and a de-excitation. Right? But okay, let me just save this let me just save this picture for now. Let me tell you one thing. I forgot to tell you one thing. All right. So supposedly, if you drive this for a long time, it should just oscillate without an end. Right? According to this equation. Yes? But this is not what we see in the experiment. You can ask them. They've done the experiment last week, right? This is not what you see. What do you see? Flattens out, right? Okay. So it flattens out. Now, the question is, does it flatten us out here or does it flattens out somewhere close to here? Or does it flattens out to a specific volume?
It's like somewhere up there. I think. It doesn't go to 0.
It doesn't go to 0. Yeah?
Yeah. Yeah.
So would you say it's in the middle or above the middle or below the middle? In terms of the oscillation amplitude.
I don't know. I think probably escalation is this week.
No,
It's
that was last week. Not 3B.
I'd say above 50%.
Above 50%?
Yeah.
Okay. If you drive it long enough, it's supposed to stop at 50%. Okay? It's supposed to decay like this. Yes? And why is that? Okay, why is that? That's where I want to use my marble picture. So now let's come back to the marble picture. Okay. So if my ground state and my excited state are just two buckets, and the excitation and the excitation is just to shift population from one bucket to another. If that's all, okay? If that's all, then I can describe it with a rate equation, right? So the increase of the excited state population is the more population you have in this bucket, the more likely you're gonna lose, right? You're gonna lose it due to the excitation process. So the more marbles in the ground state bucket will give you more chance to increase in number in the excited state population, right? Okay, so this is the same coupling coefficient, so let me just read G and G. Okay. The same with the ground state. Just the opposite. The ground state also goes like this. The same logic. Yeah. Now, let's see. Now, this will turn out to be an equation that is exponential. Maybe like this, like this. Okay. So maybe this is 2. Maybe this is half this. Okay. So if N0 is the initial population, if the N0 is the initial population in the ground state, okay, then the excited state will go up like that, and the ground state will go down like that. Okay, so this is what this equation tells us. Okay, it will approach to 50%. Why 50%? You can see it from another angle. In the dynamical equilibrium, we have no population exchange, right? What you lose here is equal to what you gain, right? Each bucket is taking marbles out, putting marbles in a dynamical equilibriums. There is zero change here. That means zero change here means NE equal to mg. NE equal to mg. This is dynamical equilibrium. Okay, and now we, on the other hand, we know the total number of marbles needs to is conserved, right? So by this we know NE equal to NG equal to 50% of the initial population. Yeah. So by this dynamical equilibrium argument, we can know that this is how it's supposed to be. Okay, we just don't know the functional dependence being an explanation or something else. Okay, but this is expected classically. Okay, so classically, if we just have this exchange of marbles, then this should be the outcome. It should saturate, not at the highest level, not like what we talk about 100%. It should saturate at 50% level, and it just stay there. It doesn't matter if I drive this for indefinitely long. It will just stay there. It will not respond to my drive anymore. Saturation. Okay. So why are we seeing this? Why are we seeing this? We are seeing, or in other, or maybe, why are we seeing this? More than 50% population. What's the reason for that? Think about it. That is because of quantum interference. Okay? That is because of quantum interference. If I would give a picture to it, I would say there are more than one way to drive the particle to the excited state. Right? How? I can go once up. Yeah? Or I can go up, down, up. Yes? Or I can go up, down, down, up. There are a lot of different ways to go to reach the final state. And all this path coexist in the quantum mechanical world, in a quantum mechanical regime. All these possible paths, they can be in superposition, they can coexist. And that's what gives you this. Constructive interference, 100%. Constructive, destructive interference, 0. Okay. So the 0 knot and the 100% knot, these are the result of quantum interference between different excitation paths. And over time, the quantum coherence is lost. The quantum coherence between different paths, they are lost. okay? And they can no longer interfere with each other. And that's why you start to lose this oscillatory behavior. And then you transition to the classical behavior. So what we are seeing here is decay. It's actually a quantum decoherence. It's actually a quantum decoherence transition. Because we lose coherence over time due to our interaction due to the interaction between the quantum system and the environment. Okay? So this is full coherence, this is partial coherence, this is incoherent. Yeah? Remember we talked about this in the beginning of the lecture. Full coherence, partial coherence, and this is incoherent. Yep. Okay. So that's the reason we have this. Okay. Another way to I'm sorry. Let me take it back. Let me take it back. I was thinking about some kind of perturbation picture. Let me take it back. Let me just say, when we were driving it, still the same story. Full coherence, partial coherence, and incoherent, but just different picture. When we were driving it, we drive it. So if you don't look at the ensemble, just look at one single MV qubit. Okay. When we drive it, there's a large chance for this qubit to be. There's a small chance for this qubit to be in the excited state when we first drive it. When we drive it for longer, there's a larger chance for this qubit to be in the excited state, right? When we drive it for long enough, like here, P0, there's a very, very large chance or full chance for the MV qubit to be in the excited state, and no chance for that to be for the qubit to be in the ground state. Okay. Now, when we are in this, before we reach the 50% limit, like here, okay? But before we reach this is already past the 50% limit. When we're here, and we have a little excitation, okay? So say this is 20%, this is still 80%, right? The system is in the quantum superposition of both states. Yeah. And now this state can continually be drive up. But I also have some chance to be in the excited state, right? And it is possible for that part of change to be driven down. To be driven down, correct? So should I go up or should I go down? In this first half, the phase of these two paths adds up constructively. So it goes up. It can exceed the 50% limit because they add up constructively. When I de-excited it, right? The same story happens, but like reversed. And when I'm here, when I'm 50%,
when I have 50% here, 50% here, should I continue to go up or should I go down? Oh no, should I continue to go down or should I go up? Right? This point. And at this point, these two paths interfere with each other. And the result is it goes down. They destructively interfere with each other, and the result is it will go down. So they will drop below the classical limit. Okay? So this is deviation from the classical limit. And these are the result of Coulomb interference between the between two processes. Okay? And that is because the quantum superposition, the quantum coherence between the excited state and the ground state. Okay? There is another form of, let me just write it here. There's another form of Schrödinger equation. It's called optical block equation. Next week we will cover this. But this is just another form of Schrödinger equation. You can use different symbols and blah blah blah. Okay. This turns out to be very useful. And this is a set of three equations. We'll just write it down here. U. I just want to point out that this equation, later we learn about UVW, or the three-dimensional coordinate of the block vector. Okay, and they represent these two represent the quantum coherence, and the last one represent the population difference. So P, it's like NE minus NG. Okay, in this case, or it is like PE minus PG. All right. So you can if we just look at the population here, if we just focus on the population change, you see that this has actually a very similar form to the ray equation, right? Because the ray equation here can be cast into this form. Right? So if we call this population difference as W, it's W. Right? So this has pretty much the same form as this. So without this term, this is basically the same as the wave equation. And it will just do this, do the exponential saturation at 50%. But with this term, this will oscillate. And this term, V here, represent the quantum coherence. So when you still have quantum coherence between the ground and the excited state, the population will be oscillatory. When you lose all the quantum coherence, then it will become a saturated curve line. Okay. All right. So that's the coherence. All right. So that's the end of today's lecture. Not too bad. 2 hours. Okay, we start a little late. Okay, now we can, thank you very much, and you can now move to the lab. Oh, quick quiz. Oh man, never stop. This is important. Let me just write it down. Let's get this over with. This is important. Quiz. Is Rabi oscillation a result of quantum interference? That's the first question. Let me just write the questions. Is the this is harder. This is harder. Is the Rabi spectrum? Spectrum means excited state population as a function of frequency. Okay, so that's a spectrum. So when you change your frequency, but keep your drive duration the same, keep your strength, keep your microwave power the same, but only change your microwave frequency. After waiting for the same amount of time, how much excited state population you can have. Okay, that's called the Rabi spectrum. And earlier we saw that from the formula, it is the amplitude, it's in the amplitude of the population, right? So it's basically a Lorentzian. It basically has a Lorentzian form. Is the Rabi spectrum width equal to the qubit, okay, which is natural line width. Okay, natural line width means decay. So how much time it takes if you put your qubit in an excited state and you just wait, how long does it take for this to decay? That time, the inverse of that time is called the natural line width. Okay? Right, so that's this. That's a qubit natural line width. So for the first question, yes or no? Okay. Come on, move. For the first question, yes or no? Alright. Everybody? Yes, correct. It's no. Alright. So let's move immediately to the second question. I think this is more challenging. Is the Rabi spectrum width equal to the qubit natural line width?
So qubit natural line width was the time of decay.
Time of decay, the inverse of time. So if the time of decay is 1 millisecond, then the line width will be 1 kilohertz. Okay?
And can you say again what Rabi spectrum is?
Rabi spectrum is the population, the excited state population as a function of microwave frequency. At a given amount, at the same given point, if you wait for a fixed amount of time, right, and you drive it with different frequency, yeah, at this time, what will be the excited state population? It's supposed to fall as a function of, it should supposed to change its position as a function of frequency, right? Okay. Is this the same as this width. So that's the spectrum. Sorry, that's the spectrum. So that spectrum basically looks like this. Is the width the same as the natural line width of the qubit?
I'm still confused. What's the Rabi spectrum?
We took the spectrum last week, right? You drive, you measure the population.
Yeah.
As a function of omega. So that's the Rabi spectrum. You give a pulse for a fixed amount of duration.
Yes.
But you change the oscillation frequency inside
Yes.
the envelope, right?
Yes.
So as you change the oscillation inside of course you get the maximum at the resonance when you're on resonance. You get the maximum population, right? When you deviate, you get less,
Yes.
right? So there's a distribution, correct? This is what you see, right? In your experiment. I'm asking, is the line width here the same as the natural line width? By the way, in the formula we just gave, there was no, it was under the assumption that the drive just continue on indefinitely. Okay, in the formula that we just gave. So don't refer to that. Okay, that's the simplest case. So this is a post excitation. That was for continuous excitation. Okay, these two are slightly different. Okay, so don't refer to that. So it's basically I'm asking if you have a post excitation. And I'm going to refer for a post excitation. If you have a post excitation, since we don't have a machine that can turn on forever, right? So at some point we have to shut it down, right? So I mean, practically it is a post excitation, no matter what. So if you have a post excitation, that width you measured, you try to measure the resonance, so you scan the frequency. You don't know what the resonance is. You scan the frequency. You have the width. Is that width the same as the natural line width? In other words, this decays after a certain time, right? So is this equal to 1 over E decay? Yes or no, or depends. Yeah, we give you 3 answers. Yes or no, it depends. Okay. Well, you need to give me a reason if you say depends. Or you need to convince other people. I like your shirt, by the way. Is that a volleyball team? Yeah? Cool. So everybody choose no? You choose no.
Yeah.
You choose no. 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 Or you're not sure.
I'm not sure.
So you say it depends. Common sense. What about you? We know. And you say no. Okay. Alright. At least we have someone who opposes all of you. Can you try to convince them why?
Is that the natural language is kind of frequency domain spectrum? This direction. This and
Yes.
and this is proportional to
Yes.
temperature. And
So
here,
it's 1 over 2.
about this, you can, if it's on resonance, the spectrum entanglement like this, and if a body tune, then it exponential decay will be faster. So I think
So you, what's your argument? Just say it again in a more succinct way. Try to convince them. Maybe you're right. Then you're teaching them a lesson, something new that they don't know.
this has depends on the detune. If you detune like the laser detune, I think the gamma will change.
Okay.
Because the location here. And if your quartz is on resonance, the decay rate of this large oscillation will be smooth and have body tune.
The decay rate will be faster. Is that correct? He does have a good point. He's arguing that, you know, this, when they do the experiment, this seems to be a short time. That's your point, right? This drop seems to be a short time. So like maybe an order of a few hundred nanoseconds. If one cycle is 1 100 nanoseconds, this is probably like, I don't know, 400 nanoseconds. So you're saying this time is long compared to the natural time, natural decay time. So the excitation spectrum should be 1 over 400 nanoseconds instead of 1 over 1 millisecond. Is that your argument?
I'm pretty sure.
All right. So the answer is depends. It's actually a very complicated issue. Okay. The true. Okay, you can sit. The true resonance will have a little width. Okay, the true width resonance will have a little width, and that width is corresponding to the natural line width. That width is called the natural line width, and it corresponds to the decay time. So this one is 1 over 1 millisecond. Okay? Yes. Now because we are using the pulse. The pulse, since it's not like indefinitely long, it's not a monochromatic source, correct? The Fourier transform, the Fourier spectrum of this pulse is not one line, but it is a distribution. And that distribution is the inverse of your pulse duration. Okay? So naturally this pulse covers a bunch of frequencies. Yeah? So when you scan, so this is the frequency spectrum. When you scan the frequency of the pulse, microwave pulse, you're moving the whole thing. Okay? And if this is, here is the natural line width, then you can start to excite it. You can start to excite the qubit already at this detuning, right? Because you have a bunch of frequency components in your pulse, and a small portion of that is the same as the natural line width, right? It's the same as the resonance frequency. And as you move closer and closer, it becomes this portion, the component in the resonance becomes larger and larger, so naturally it goes up. So therefore your major spectrum will mimic your pulse shape. Okay, this is called a transient effect. Okay. Now, if you are able to increase this,
for a long time. To longer and longer, and you shrink, you make it more and more monochromatic. Then theoretically, you're supposed to recover this at some point. If your pulse duration is longer than the natural decay time, you're supposed to recover this natural line shape. Okay? However, here's another problem. Because of the decay, this coherence effect, there's also another width associated with this 400 nanosecond. So at some point, you're stopped. Even though your pump is drive this for a long time, and you're supposed to drive it like this, right? But because of this decoherence, it will appear as if your pulse is only 400 nanosecond. Yes? And your Rabi frequency will not continue anymore. Okay? So it gets stuck at 400 nanosecond. Yes? Okay, so unless you have like super long coherence and super long pulse duration, longer than the natural line width time. Otherwise, you will never recover the natural line width. You'll never see it. Okay? All right. Cool. So this is actually a critical point in our next lecture. All right. See you later.
Is it still recording? Oh. Oh, I don't know why this is not working.